All right, welcome everybody to the first day of MCAT Prep Course. We're going to be starting with Gen Chem, and so the way this class is going to go is we'll start with Gen Chem, then we'll go to OChem, and then biology, biochemistry, and then physics. For physics, I might move it to after OChem, but for now I'm keeping it at the very end just because I don't want to do like all of Chem Phys at once and then hop into bio. So we'll see how it goes, but thank you everybody for joining. And yeah, also this we're starting with the basics, right? This is Gen Chem, and so like at some point you might feel like this is very basic. Like you guys already know this stuff, but just I would just stick with it. You know, you guys are free to like not join. It's up to you guys, but it's good to start from the beginning all the way to the end because you guys might feel like you know something, but there's always something that you either didn't know or you forgot. So once again, it's up to you. But thank you guys for joining. All right, so first thing we're going to talk about is atoms, right? Atom is like the building block of everything, right? Of life, non-life, all of that stuff. So the very first, like this is some history, right? The very first like model of an atom was just a billiard ball model, right? Also, you guys don't have to write this. This is a little background. I'll tell you what part's important. So we started with the billiard ball model. This like it doesn't tell you much. It just tells you that there's different atoms, right? Some atoms are big, some atoms are small. They have different masses. You know, some are heavy, some are really lightweight. But this doesn't really tell you much, right? So the next model was this right here. Some of you guys might remember the plum pudding model. This is the Thomson plum pudding model. These negative things, right? This shows the presence of electrons. So this was the first time that the electron was discovered, right? Giving a negative charge to the atom. But this is still like insufficient, doesn't tell you much about the electrons other than that they exist. Now over here, right? Let's see if I can draw this properly. This is called the planetary model. This ball in the center is nucleus, right? So with this model, it shows that there is a central nucleus with an overall positive charge. And what makes that positive charge? Protons and neutrons. Neutrons don't add to the charge, but they're just there. So remember, the nucleus has protons and neutrons. Now, what are these things? These are just like the electrons on the outside. They're orbiting around, right? Just like a solar system, like planets and stuff. But the issue with this, anybody know what the issue with this one is? This part's like somewhat important, but I'll cover it right after. But anybody know what the issue like with this model is? Yeah. Exactly. Yeah. This one in this model, the electrons, they're all like equally distant from the nucleus, which we know is not true. So then the next model is the Bohr model. This is the second most recent model, right? Pretty sure all of you guys are aware of this one. This is your like nucleus, right? Now this brings up the idea of different levels, right? Different like clouds or whatever you want to call them. Then the closer to the nucleus they are, the lower in energy, but the further they are, the higher in energy. So this introduced the idea of like quantized electron levels. This is also important because when you go from, let's say like, okay, this electron right here, if you want to move it to an outer level, right, is this going to, what is it going to do? Absorb or emit energy? Yeah, if you're going from like level 2 to level 3. Yeah. So when we say it goes to like an outer level, this means let's do like L to H, right? This is low to high level. This is going to absorb energy. So it takes energy to push it to a higher energy level. And when we go from a low to high level, it just becomes, we call it excited. So this is the excited state. If at any time you can't read my handwriting, just let me know. I have really bad handwriting. Okay. So then the opposite, right? If we're going to go back to the original level, this is high to low. This is going to do the opposite, which is emit or release energy. And this is like, going back to ground state. Okay. And, once again, this is not the most recent model, but this is like a concept to just know, like, changing energy levels. But now when we talk about the most recent model, this one, I don't really know how to draw properly, but like, I'll explain it real quick. Oh my God. Okay. So these like ovals that I have inside, basically like, you can't ever tell that an electron is in a certain spot. You can't pinpoint the location of an electron. you can only know the probability of it being in a certain area, right? This is like the, I think, quantum mechanic model. So like these like ovals, right? They represent like an area of like probability. In this area, there's like a 90% chance that there's an electron there, but you can't tell like the electrons right here, over here, over here. This is a really important concept to know, right? Once again, you can't ever tell the exact location of an electron, just the idea that it might be in this area. Okay? So that is it for the atom. These boards don't erase properly. All right, so the atom, right? What do we have in the atom? Like, what makes it up? We have protons, electrons, and neutrons. So protons, I read it P plus because they're positively charged, then neutrons, and then electron E minus. This is kind of like a foreshadowing to physics, but what is the charge of a proton? Anybody know? So it's a positive 1.6 times 10 to the negative 19 coulombs. And then electrons, the same thing, but opposite, negative 1.6 times 10 to the negative 19 coulombs. And then neutrons, they're neutral, they have zero charge, so it's zero, right? No charge. This is why in the nucleus, the positive charge comes solely from the protons, right? You can have 100 neutrons, but the charge will just be based off the protons, okay? Now, yes, protons and electrons have charges, but the mass comes from protons and neutrons, okay? So this is like one way of writing elements, right? X is like your element. This is going to be the atomic mass. And then Z is your atomic number. So for example, if I have a carbon, let's do like this, okay. Based on what I just said about what contributes to mass, what would this be? Like, how many neutrons do we have here? Or do you guys even know, like 12 and 6, what does that even mean? Also, anybody on Zoom, you guys can respond too. I have my AirPods in to listen. Yeah, so like, if this is the mass, and do you guys know what atomic number is, by the way? Atomic number is just going to be number of protons, okay? So this means you have 6 protons, and if your overall mass is 12, what is the number of neutrons in this specific carbon? Yeah, it's just 12 minus 6, which is 6, okay? What about this one? We have 13 mass, so it's just going to be 7 neutrons, right? And then carbon 14, right? You can write this like several different ways, like carbon. These are called isotopes, by the way, right? Like, the number of neutrons in like mass overall will change, but it's still a carbon. Why is it still a carbon? Because this right here, the atomic number, right? This cannot change, right? Only the atomic mass can change. But as soon as you change the atomic number, like you put a 7 down here and you keep it 14, right? This is not carbon anymore. This is nitrogen, the very next element, okay? Because once again, the atomic number, the number of protons an atom has is characteristic of the atom, right? Or of the element. So that's very important. And this is like going to be one of the last, I think, chapters of physics where we talk about, radioactive decay. You'll see like when you have different decays, the atomic number will change and you'll have a completely different element, okay? But the key point here is that if you keep the atomic number the same, but the atomic mass is different, that's just called an isotope. Isotope just means different mass or different number of neutrons. Okay, so everybody's heard of the term mole, right? MOL or MOLE? No? Okay, anyways, a mole is just like if you think about, let's say like I weigh a ton, right? What does a ton mean? Ton just means 2,000 pounds, right? It tells you the amount of something. If I say I have a dozen, right? I have 12 of something. So a mole is just another way of saying amount of something. And what is that amount, right? 1 mole equals 6.022 times 10 to the 23rd. This is Avogadro's number, right? 6.022 times 10 to the 23rd of what? It's going to be anything, right? Molecules, particles, ions, just anything like that. we refer to things in moles because obviously, there's a bunch of molecules in like one thing. So it's like you just use mole to make everything simple. Um, but you still need to know this, right? Because sometimes you'll be asked something like how many molecules are in this overall compound, and you have to be able to convert. So this one, definitely just memorize it because 99% sure you're not gonna ever get it, given to you. So just keep that in mind. Um, when we look at our periodic table, the mass that you're given is the mass of 1 mole, right? So same example, carbon. I think it's like this, right? 6, and then it gives you like 12.04 something. The 6 is your atomic number, obviously, and then this is the mass of 1 mole, not one molecule, but 1 mole. So it's very, very simple. We call that molar mass. And then I'm gonna give like a quick like question asking to find out like how many moles in this and this. But first, I want to introduce the idea of dimensional analysis. Okay, dimensional analysis. Some of you guys call it the railroad method, or I don't know, race, whatever you call it, right? But dimensional analysis is just like how you convert from one unit to another. Also, by the way, if I'm ever writing something and I erase it while you guys are writing something, just let me know and I'll stop. You good? Okay. So obviously this is not MCAT related, but let's say I want to convert 10 days into hours. No, let's do seconds. 10 days into seconds. I know some of you will probably know how many seconds are in a day, but like just pretend you don't. How do we do this? We're going to start with our starting unit, right, which is days. Now, I want to ultimately get rid of days and end up with seconds. So to get rid of days, you're going to have days down here. And let's say like I only know how many hours are in a day. So I'm going to put hours up here. Okay. In one day, there's 24 hours. So now, obviously, there's more to this, but when you do this, you can cross out days because this is just multiplying and dividing, right? So this will get rid of days. Now, we're not there, right? We want to go to seconds. So to get to seconds, oh my God, slanted. What the hell? Okay. Next, we're going to convert hours into minutes, right? I know, like, once again, you probably know how many seconds are in an hour, but I'm just giving the example of like how you can take this all the way down, right? So in 1 hour, there's 60 minutes. And then finally, in 1 minute, there's 60 seconds. Okay? So once again, look, I started with days. I cross it out because it's on the numerator and denominator. Hours, same thing, cross it out. Minutes, cross out. Now I'm left with seconds. I converted all the way from days to seconds. And then from here, all you have to do is just multiply, right? Multiply. There's nothing to divide by because it's just one, but this is like the dividing area. Um, so like this is one way to do it. I mean, it's the same way, but like another thing that's very important is to keep things in scientific notation if possible. It just makes it like easier in my opinion. So how I would do this would be like this is 10, I'm just put 1 times 10 to the 1. And then 2.4 is going to be times 24 is going to be 2.4 times 10 to the 1. Whoa, this is really slanted. Sorry. Wait, 1 times 10 to the 1 times 2.4 times 10 to the 1, and then times 6 times 10 to the 1, and then again times 6 times 10 to the 1. The reason I do this is because you can just look at all the 10 values, right? There's like 4 of them. So it's going to be something times 10 to the 4. And then you just multiply all the non-10 digits or numbers, right? 1 times 2.4 times 6 times 6. So 36 times 2.4, it's, you can estimate and stuff, but, I'm just saying like this will help you a lot. I think it's like 86.4 or something like that. 86.4 times 10 to the 4th. All right. And then if you want to really be scientific notation with this, then you can keep it like this. Okay. So you end up with 8.64 times 10 to the. Okay. So now the reason something like this is important is because this is in seconds. If I want to convert it to something else like milliseconds or microseconds, you don't deal with that with seconds, but I'm just saying you can easily convert, right? I think we'll talk about this more like later on, like conversions of different units, unless you guys want that right now. But for example, if I want to convert this into, say, milliseconds, you just multiply it times 10 to the 3, then you end up with 8.64 times 10 to the 8th, stuff like that. In my opinion, it's really simple to just keep in scientific notation. Sometimes your answers will also be in scientific notation. like your multiple choices. So just definitely get in the habit of this, and yeah, it'll be helpful. So now using like this, like is everybody good? Like everybody knows dimensional analysis? Okay. I'm gonna give you guys like a practice question real quick. This is gonna involve like the moles and stuff that we just talked about right before. All right, let's see. So, all right, I want you guys to tell me how many molecules are in 48 grams of carbon. So, how many molecules are in 48 grams carbon? And just to be nice, the molar mass is 12 grams over moles. So I'll give you like a minute to do this one, and then I'll solve it. Okay, so 48 grams of carbon, right? The first step. Actually, what did y'all get? Anybody get the answer? Even once again on Zoom, you guys can respond. What'd you say? Okay, what about y'all? Okay, and then I think someone was saying something on Zoom or not. Okay, so basically what we're gonna do is 48, right? We're starting with 48 grams, and then we want to convert this into moles because that's the only thing we know how to convert to right now, right? There's 12 grams over here, and you got moles up here. This is 1 mole. Now remember what I was talking about? 1 mole equals six. It's 6.022, but it's MCAT, right? You just round, save time, so it's 6 times 10 to the 23rd. And then once again, right? It can be anything, molecules, particles, all of that stuff. And then you can just do like 48 divided by 12, which is 4. And then you have 4 on top times 6, gives you 24. Why do I write so slanted, bro? What the hell? So you get 24 times 10 to the 23rd, which is also 2.4 times 10 to the 24th. I think that's what y'all got, right? You just had it in 24. And then what did you have? Oh, that's fine. How was your exponent, though? Was it good? Okay. Yeah, once again, like rounding and stuff will give you slightly different answers, but like your answer choices are going to be very, very far apart to where you can tell even if you made a small mistake. Okay. Um, one more question. Okay. So now let's say we have. Hold on, I forgot the question. Okay. So you have this many particles of barium chloride, right? BaCl2. Tell me how many. Wait, shit. What are we looking for? How many? Okay, how many grams of chlorine of just Cl, right? So we have barium chloride, which is a compound, and we just want the grams of chlorine alone. Yeah, the molar mass for chlorine will be 35 grams per mole. Sometimes they do give you the molar mass on the MCAT, but like other times they don't. But the reason I'm giving it to you is because you might not have a periodic table on you. If they don't give it to you, then just look at the periodic table that's given to you, and you can just get the molar mass from there. Okay, so first thing, right, we're starting with the number of particles they give us. So this right here. And then, this is, I'm sorry, particles. I'm gonna write part, okay? Then particles, right? We know it has to deal with Avogadro's number. So to find number of moles, remember this is particles of BaCl2, right? Not chlorine. So make sure you write that down. I'll write it from here on. But next, right, 6.022 times 10 to the 23rd particles equals 1 mole of barium chloride. Okay. Now, we're being asked about chlorine, not barium chloride. So in every molecule or every mole of barium chloride, how many chlorines are there? This right here, it's a 2, right? This is something you have to look out for. The ratio of chlorine to barium chloride is 2 to 1. So We're going to convert moles of BaCl2 to Cl. So we have this right here. See how this makes a difference? Because if you just kept it 1-to-1, you would get half the answer. So then from here, simple. It's 35 grams per mole. So 35 grams, you just multiply, right? Grams per mole of chlorine. And then this is pretty chill. Like this 10 over 23 or 10 to 23 will cancel out. It's just this will equal 2, right? Dividing this by this. So you get 2 on top times 2 is 4. And then times 35 will give you 140 grams of chlorine. Anybody have any questions on like this or just dimensional analysis or anything? Okay. All right. And am I good to erase this? Okay. So, guys, this was not even chapter 1. I'm not gonna lie. This was like chapter 0. So now we're about to start actual chapter 1, which is like atomic structure. I mean, part of the stuff we did was obviously like related, but according to Kaplan, it's not chapter 1. So, chapter 1, like I mean, the very first thing is like dealing with waves and stuff. So I'm gonna draw this out right here. Okay. So here's a wave. Obviously, it's gonna keep going. Let's see right here, right? It's gonna be our amplitude. It's like the top to the bottom, right? This is like your 0 points or the highest. What is this highest thing called? It's called the peak. And then the bottom, the very lowest part, is the trough. I don't think that really matters, but obviously it's just basic information. Now when we're talking about like wavelength, right? Wavelength, you just like you basically look at the point, like how far is it from the exact same point, right? What do I mean by that? The most common way to check wavelength is peak to peak or trough to trough, right? But peak to peak right here, okay? This is going to be your wavelength, and we denote it with lambda. And the reason I said what I said before is like, let's say you didn't want to use peak or like somehow couldn't use it, then just let's say we start with this peak, this point right here, okay? The same point is going to be over here, right? This point goes upwards, right? This point does not, it goes downwards. So these two are not the same. But when we reach this point, it's the same thing, right? It goes up and then continues on. So even this right here, from here to here, will also be considered a wavelength. So just preference and like whatever is possible. And then wavelength, right? Wavelength is in meters. Shit, the hell? Okay, wavelength is in meters. Now, let's talk about frequency. Frequency, sorry, F. Frequency is basically number of cycles per second. So this is like 2 cycles, right? Because we went 1, 2. So if this took like 3 seconds, 3 seconds to go 2 cycles, right? The frequency is going to be 2 over 3. It's 2 cycles per second, but cycles is not really a unit. So that's where the unit hertz come from, right? Hertz. A hertz is just an inverse second. It's just 1 over second. So as you can see, right, we had cycles per second, but if you get rid of the cycles, it's just something per second, so it's hertz. Why is it so slanted? Damn. It's because I'm writing like sideways, I think that's why. Are you guys good though? Like it's not like affecting anything? Okay, I'll try to fix it from here. Anyways, this is your frequency is gonna be number of cycles per second, right? Now the opposite of that, or the inverse, is gonna be your period, okay? Period is seconds per cycle, right? So like in one cycle, right? How long did this take to go from here to here? It's just gonna be the opposite. You flip it, right? It's gonna be 3 over 2, which is like 1.5 seconds. So it takes 1.5 seconds to complete one cycle. And then we denote it with the T, unless it's some Greek letter. I don't even know. But it's like a capital T. And then speed, right? Speed is you can call it like velocity, like V. speed is measured in like meters per second generally, right? It's just distance over time. And so the way you can find this is like multiplying lambda, which is your wavelength meters, times frequency. It's meters times inverse second, right? Meters. Why do I write m's like that? Okay, meters times 1/2 just gives you meters per second. So that's kind of like where it comes from. Um, and a very important speed to know is the speed of light, which we mark as c. So you can even write this as c equals lambda f. But in some cases where you're not given the speed of light and you have a completely different speed, same formula applies. So speed of light, anybody know it? Yeah, 3 times 10 to the 8th meters per second. And so if you're dealing with like light and your frequency increases, then your wavelength is going to decrease proportionally to match the speed, right? And vice versa. But I guess the main point to note is that your frequency and wavelength, they're inverse, right? So if you have something that's really high frequency, the wavelength is going to be low, right? Because it's easier for it to complete more cycles if it's a small wavelength. And if your frequency is low, that means your wavelength is high. So it takes longer for like a full cycle to complete. Does that make sense? Okay, this next part is like it's like I don't know, it's like tedious, but there's different types of like electromagnetic like waves, I guess you call them. Um like okay, for example, the lowest wavelength and highest frequency, we have like gamma, X-ray. This showed up on my MCAT, so like it's good to know. Okay. Like a good mnemonic for this: giant xylophones usually vibrate in my room, right? Giant xylophones usually vibrate in my room. That will just tell you like the first letter of each of them. Now gamma rays, all right, I need to write these exponents bigger. So yeah, like these fucking exponents, they're like just like know the general range. Like obviously, it's not like every like X-ray is literally from 10 to the negative 12 to 10 to the negative 8. It's probably something like in between, but like you don't have to know the exact values, just know the range. And I think the more important aspect is knowing which of these is longer, which of these is shorter. Once again, this is the shortest wavelength, which means highest frequency, shortest wavelength. Okay. For visible light, visible is like literally what we can see. Once again, as I was saying, this range is like kind of it's not exact because visible light goes from 400 to 700 nanometers. We typically call them like we typically refer to them in nanometers. But if you're ever doing any calculations, make sure you convert back into just regular meters, right? 400 to 700. 400 is going to be like purple or like violet, right? And then 700 is going to be red. You guys know like Roy G. Biv? That's just the order. Or if you want to do it backwards, like Bib Yor, something like that. Okay. So violet or purple, whatever you want to call it, is going to have the shortest wavelength, highest frequency, and then orange and red going to be the highest wavelength or longest wavelength and shortest frequency or lowest frequency. Another thing I just like I guess thought of is sometimes anybody like draw or like know anything about like color theory and stuff like that? Okay, me neither. Basically like if you absorb a color, then the perceived color in return is going to be the complementary color, right? So if you absorb all of this green, it's going to appear as red. And like I know like how do you remember that? Basically, like what I do is write Roy on top and then GBV. Don't put the indigo, just put GBV. These are the corresponding complementary colors. Not to spoil or anything, but I think they showed up on a section bank or something. So if you absorb all of red, you're just gonna look green. Or if you absorb all of orange, you look blue. That type of stuff, right? Just know like these basic like complements stuff. It will be helpful. And I haven't even seen this anywhere. I just made this up. So like maybe you guys learned something new from me that you wouldn't have learned from anyone else. Okay. Now I think like one of the highest yield like formulas to know. Let me get a let me get a different color. Anybody know what I'm about to say? We're talking about like wavelengths and stuff. Energy. So we have energy equals HF or energy equals HC over lambda. So H is going to be Planck's constant, right? Erase this. Okay. Planck's constant is 6.626 times 10 to the negative 34th. I don't remember the units. I forgot. It's like, I think it's joules times second or something. I think. Um, anyway, 6.626 times 10 to the negative 34th, right? And then frequency is frequency. The reason there's two formulas here is because if you have frequency, then just use frequency. If you're given wavelength, you still have everything you need, right? Because h is a constant and c, once again, is a constant. It's the speed of light, which is 3 times 10 to the 8th meters per second, right? So using this, I want you guys to tell me, like, what is the like energy of 700 nanometer? Like if you like release 700 nanometers like light, what would the like energy be associated with this? All right, so I'm sorry, you guys still working? You guys good? Okay. So what are we given? We're just given wavelength. So we're gonna use E equals HC over lambda, right? And like from here, it's just 6.6 times 10 negative 34 times 3. What did y'all get, by the way, before I give the answer? You mad wrong. Mad wrong. Yeah, what were you saying? No. Or maybe, hold on. Okay. Yeah, that's correct, actually. I think you're right as well. I just wrote it wrong on my thing. That's crazy. Okay. So, yeah, so we have this, and then yeah, the main thing here, once again, when you're dealing with like visible light or just anything in nanometers, convert it into meters. So like 700 nanometers, I'm gonna write that as 7 times 10 squared. This is nanometers. I'm gonna go over like the different like prefixes, right? Like nano and all that. But let me just solve this first, and then we'll do that. So it's 7 times 10 squared, right? And then to get just meters, you're doing 10 to the negative ninth. So you get 7 times 10 to the negative 7 meters. And then just like, yeah, I feel like solving this. It's like, 20-ish for 7. And then when you divide 20 by 7, just round to like 21, right? You'll get like, it's going to be like 2 point something, like 2.9 or something, but like, we'll just estimate and say 3 times. Okay, this is where I messed up when I was writing my notes, but just keep track, right? You're starting with 10 to the negative 26, and then you're dividing, right? When you divide like tens with exponents, you're subtracting the exponents, right? So it's negative 26 minus negative 7. So you get 3 times 10 to the negative 26 plus 7, which is 3 times 10 to the negative 19. And this is in joules. So yeah, I guess on that topic, I guess it's really important. I think I was gonna mention it in physics, but like that's really long away, so I'm just gonna mention it now. Let's say I'm gonna use like meters, right, just as the base, but this could be anything. The I guess okay, kilo, right? Is there anything else we do before that? No, probably not. Okay, so kilo, right? So kilometers. This is like 10 to the 3, right? This is like much bigger than meters. We're going the positive side. So kilometers. And then after that is mega meters. I know this is like weird, like you don't see this, but this mega, I'll just write like this kilo, mega. Mega is going to be 10 to the sixth. And then we have giga, which is 10 to the ninth. And then we have tera, which is 10 to the 12th. I always mix up mega and giga, but like the way I would say to remember this is if you guys deal with like files on your computer, um, like I know you're probably aware, obviously terabytes super big, and then gigabyte is way bigger than megabyte, right? Like if your video is like 10 gigabytes, you're like, what the hell is going on? But if it's 10 megabytes, it's not that big of a deal, right? So you can kind of like use that to remember which one is bigger. So gigabytes bigger, right? Or just giga in general, mega, kilo. It's all going by three, okay? So you can just go incrementally like that. Now for this side, I don't think you really see this, but like D, right? This is deci, which is like 10 to the negative 1. The only time I've seen deci is decibels, like when you talk about like how loud something is, but you never convert it into just like bells, right? It's just always decibels. So you don't really need to know this, but just I guess it's good just in case. Now centimeters or just centi, this is 10 to the negative 2. And then wait, is this still good on Zoom? Like it's not going far off, right? So let me know. So we have milli. Okay, 10 to negative 3. And then from here, we're just going to go by 3. So we have micro. This is a mu. So micrometers is 10 to negative 6. And then nanometers, at 10 to the negative 9th. And then the furthest we'll ever go is picometers, which is 10 to the negative 12th. Yeah, I think that looks good. This one, I don't really have like a way to remember it. I don't know. I don't think it's that hard to be honest, but like after you deal with these a lot, you just like get used to them and remember. But at least you should know milli is like negative 3, right? And then there's not too many after that. Okay. So something I guess really quick I want to mention is how we were talking about that model like this one, where like you're not really sure where the electron is, you just know the probability of it being there. This involves something called Heisenberg's uncertainty principle. Once again, Heisenberg uncertainty principle, just going to be the idea that you're uncertain where exactly an electron is. You just know it exists in a space somewhere there. Like maybe 100% chance of it being here, but we don't know is it here or here. These like principles and like later on in physics when we talk about like laws like Newton laws, thermodynamic laws, just like I know it's like annoying, but just know them because on my MCAT and like from other people, what I've heard is like their MCATs will have like a question asking like what law or what principle does this like relate to, and so just have them like down in your head. So I would definitely write this down. I don't think I've seen this one in particular, but you never know. And there's like a few more principles like after this. Are we all good? Okay. Now we're gonna be talking about quantum numbers. I love this topic, but like it's like I don't know, it's kind of hard to explain sometimes. But Okay, start with this. So you have N, L, M sub L, and M sub S. So N is your, I don't, where should I write this? I'll write it over here. N is your principal quantum number. L is called like, it's like azimuthal quantum number, also known as like angular momentum. M sub L is the magnetic quantum number. And then M sub S is your like spin quantum number. Once again, this azimuthal, like I know it's like weird, but like just know this just in case, right? You never know if they'll refer to something as azimuthal quantum number. Anyways, right? What is all this stuff? So your principal quantum number is going to tell you the like size of your shell, right? Should I start like this? Okay, actually, really quick, let's talk about like so like this is gonna be like n equals 1, n equals 2, n equals 3. These are different like shells, right? And within a shell, you have different subshells, right? I don't want to make sure I'm like, okay, I think you guys are aware of like SPDF, all that stuff, right? Okay. So in a shell, let's say this is like n equals 3, you're going to have like a P subshell or S, P, and D. And then within these different subshells, you're going to have orbitals. And so like in this one, you're going to have like one orbital, and P, you're going to have like three orbitals, and D, you have like five. I'm just bringing this up for terminology, but I'm going to come back to this. But when I say shell, I'm referring to like one of these things, right? And then within the shell, a subshell is like, you know, like different pieces of it. And then within the shell's orbital, within the subshell's orbitals, okay? So for principal quantum number, it's just referring to like the shell, right? And the size. Obviously, the bigger the n, like if it's 4, it's bigger than n equals 3, right? So it tells you the size and the level, right? And for n, the allowed values are positive integers. So like just from 1 and on, right? So you can't have an n equals 0. The lowest you can have is n equals 1. Now your L, this is going to refer to the subshell, okay? So subshell meaning like S, P, D, F, that type of stuff. Your L, the allowed numbers for this is going to be 0 to 0 to n minus 1 included, right? So if your n is 2, then you know you can't, all you can have is 0 and 1. If your n is 1, it's just 0, right? Because 1 minus 1 is 0. Once again, I'll elaborate on this stuff. I'm just giving you guys like the quick rundown. M sub L is going to be negative L to positive L included. So if your L is like 2, from negative 2 to 2, once again, I'm going to explain what this stuff means. And spin, this one, constant, right? Spin, you can only have plus 1/2 and negative 1/2. Doesn't matter what your n is, what your L is, none of that stuff. It's always going to be positive and minus 1/2. And this refers to like the spin of the electron, right? So a positive 1/2, you're going to like denote it like this, like facing upwards, and then negative will just be downwards. So back to let's talk about this azimuthal angular momentum thing real quick. There's like, you know, we deal with like 1, 0, 1, 2, 3. We don't really go past this, but if you have an L equals 0, this refers to the S subshell. If you have 1, it's going to be P, and then 2 is D, 3 is F. So SPDF, okay? Now for S, right? A S subshell has 1 orbital. A P subshell has 3 orbitals. D subshell has 5 orbitals. Okay. Now, the reason I'm bringing this up is because this right here, this magnetic, right? If your okay, if your L was like 1, right, corresponding to P, that means that your M sub L will be -1 to 1. And what does that mean? You number the central one as 0, and then you just branch out, right? So -1 and +1. So S would be 0 right here, D is 0, and this is +1, +2, -1, -2, right? And so on. So this is like what M sub L refers to. It refers to the specific orbital, right? So once again, principal refers to the shell. Azimuthal, the L refers to the subshell. And then the magnetic, M sub L, refers to the orbital in particular. And then the spin is just plus minus 1/2, meaning that in every orbital, you can only have you can only have 2 electrons per orbital, and they have to be opposite spins, right? So you have a positive 1/2 and a minus 1/2 spin in this orbital, right? I don't feel like erasing this one. Do I have space here in the Zoom? Okay. I'm gonna erase this one though. Okay. So you guys know like how orbitals fill up or how shells, subshells fill up? Basically, like you can just use this right here, and this will tell you like the order in which electrons will fill up, right? So I drew it like this, and I'm gonna draw diagonal lines like that. And what does this mean? It means that we first hit the 1s. So we're starting with 1s, and then next is 2s. And then we start over here, we hit 2p, then 3s. And you guys see what's going on, right? So this is like telling you the order in which electrons will fill up because of the idea that this is going from lowest to highest energy orbitals. And why is this important? Because of Aufbau's principle. Aufbau's principle tells you that electrons will fill up from the lowest to highest energy, like subshells and orbitals, right? So you can't fill a 2p before you even put an electron in 1s, right? Or even 2s. So that's just like what it's talking about. The next principle would be Pauli exclusion principle. So if I have let's say this is like 2s and 2p. Yeah, whatever. This is filled up. Okay, for 2p, right? If you want to put like 4 electrons in this one, okay? You want to put 4 electrons. You have obviously 6 available, 6 spots for electrons, but if you want to put 4, you have to hit every orbital before you start putting the second orbital, right? Or sorry, second electron. So, for example, what you can't do is this. You can't just go like this. There's 2 filled orbitals, right? You have to make sure there's 1 electron in each orbital before you start putting the opposite spin one. And this is Pauli exclusion principle. And then there's one more, and this one will tell you like you can't have 2 of the same spin electrons in the same orbital. So like you can't have an orbital that looks like this, or like, right? Like this one has 2 negative 1/2 electrons. It's not right. Same with this one. This has 2 positive 1/2 ones. Can't do that. And this is because of Hund's rule. You can't have no two same spins in an orbital. Yo, did I mess this up? Hold on. Oh my god, I think I messed it up. That's crazy. Yeah, that's my fault. I'm sorry, guys. Okay, this is flipped. So this is gonna be Hund's rule, and this is Pauli exclusion. So, sorry, this is Hund's. I guess like a way you can remember this is for Pauli exclusion. It's like exclusive, right? Like each orbital is exclusive for like one of each spin. So remember it like that. Um, but yeah, we have the Heisenberg uncertainty principle. We have Aufbau, Hans, Pauli exclusion. Yeah, what's up? Mm-hmm. Yeah, it's just I don't know. It's just how it is. I mean, apparently, like 4S is lower in energy than 3D. But actually, that brings me to my next point. Let me erase this real quick. Everybody good with this stuff right here? Okay. I think I had this on one of my TikTok videos actually when I'm about to bring up. So yeah, as for once again, like why 4S is lower energy than 3D, even though this is 4 and that's 3, I don't know, but this does change. And I'm gonna draw. Let's see. Okay, I'm not gonna fill these up, but pretend they're filled up. Yes, at first you're gonna hit 3P, right? You're gonna fill all this stuff up, and then you're gonna hit this 4S right here, fill this up, and then you're gonna hit 3D and put some stuff in here. But if you have like, let's say like element X, right, and you want to remove two electrons, now you're making it a 2 minus anion. Where do you remove these electrons from? I don't know why, but like once the D or subshell starts filling up, it becomes lower in energy than the 4S. So you're gonna be removing it from here. So if I wanted X, this is X right now, right? Now I want X2 minus. I'm just gonna get rid of these. I'm gonna give you guys a little question though, real quick. So I'm gonna give you guys like some quantum numbers, and I want you to tell me like how many electrons correspond to the quantum numbers. All right, guys, how many electrons correspond to these three? How many electrons correspond to these three quantum numbers? Yes. What did you guys get anything? Or you catch the trick? Zero. And why is it? Because remember, L cannot be the same as N. The L can only be 0 up to N minus 1. So this was a dead giveaway before even like having to write anything out. You just know this one is 0. But I'm gonna give you an actual one now, like to figure out, and we'll see how you guys do. This time, let's do N equals 2 and M sub L equals 0. All right, tell me how many electrons could have these two quantum numbers. So, okay, when we have N equals 2, what does that mean your L can be? L can be, remember, once again, it's 0 to N minus 1, so 0 to 1. So our L can be 0, which is S, and then L can be 1, which is P, right? So our S subshell is going to have like one orbital, which is marked as 0, and P has 3 orbitals, but the 0, 1 is the middle one. So look, N equals 2 and M sub L equals 0. Both of these, like you can call this like S2S, right? And this is 2P. Now, we're not even told anything about the electrons, like their spin. So we can assume that we can put both electrons, right? Plus 1/2 and minus 1/2. And so we actually end up with 4 possible electrons with this. Yeah. Yeah, it's just saying like we're not saying that these aren't filled. Just pretend that they're all filled. This is like hypothetical. What is the maximum number that you or yeah, what is the maximum number of electrons that you could have? The maximum number is still 4 because that's assuming that all of these are filled up. But that's good to point out though for sure. All right, how many electrons correspond to this? All right, anybody got an answer for this one? Yes. And this one is another situation. Oh shit. This one is another situation where you don't even have to write anything out. Why? Because if you're given four quantum numbers, only one electron can have these four quantum numbers, right? Every single electron is going to have a different set of four quantum numbers. Like, yes, maybe the n will be the same, maybe L, M sub L will be the same, but you can't have four of these and say that it corresponds to two or three electrons. It's only for one electron. Because this is also very specific. It's telling you it's in the zero orbital of this subshell, and then negative one half can only be one electron, right? Because the other one will be plus one half. So, yeah, that's like another like thing. Like if you see four, then you know it's one. If you see this shit right here, where you have n equals 3 and l equals 3, you know it's 0 because you can't have the same l as the n, right? So those are like some little tricks. Let's look at. It's good if you have a periodic table pulled up, by the way. But let's talk about like hydrogen, right? No, let's do another one. Let's do beryllium. So beryllium has four electrons in its neutral state. And so when we write electron configuration, we're just writing like all of the like, you know, subshells and shells and stuff that those electrons reside in, right? So if we do this thing again, this 1s, 2s, 2p, this thing, this will once again tell you the order in which electrons fill up. So you have 1s, 2s, right? So for beryllium, the way you write the configuration is like this: 1s, 2, 2s, 2, right? You're basically saying like it has the electrons in both of these subshells, and in the 1s subshell, it has two electrons, and the 2s, same thing, has two electrons. And you can't go past 2 for s, it's going to be 2. Let's have another example. It's pretty chill. Let me see if like, yeah, I don't want to spend too much time on this one. Okay, let's look at a noble gas like argon. Okay, for argon, I know I barely like touched on this, but like anybody know what like argon's electron configuration would be? One S2, two S2, two P6, three S2, and then three P6. Okay. So it's at the very end, right? You're gonna have everything filled up. It's a noble gas. It's also like another reason why noble gases don't react because they don't have like free electrons to react with and stuff. But this is like argon, right? When you want to like find the electron configuration of something really like low in the periodic table, like what's a good one? Barium. Nah. Let's do like potassium, right? Potassium. If you wrote the electron configuration of potassium, it would be all of this plus another like 4s1. But instead of having to write all of that, you can do something called the noble gas shorthand. So all you have to do is write the noble gas that's closest to it, which is argon, and then the very next thing, 4s1, right? This is telling you that the electron configuration of potassium includes all of this, everything that argon has, plus this extra 4s1, right? One electron in the 4s subshell. And so, yeah, how would you write barium in shorthand? Try this one. And once again, like try to have a periodic table pulled up would be easier. I mean, I don't think you can do it without a periodic table actually. All right, anybody get that one? So if you look at barium, it's in period 6, right? And so the noble gas right before it is period 5 noble gas, which is xenon. So you start with like this, like X, E. Xenon consists everything, right? 1s2, 2s2, 2p6, all that stuff. And then what's new about it has 6s2. And so you see how simple this is. Like you don't have to write all that stuff out. So it's good. And like I guess yeah, like okay, I drew this periodic table because it helps with this, right? Like how did I know that we're gonna have a 6s2 instead of like 5s2 or 4s2? Because each like period, the periods refer to rows, by the way, right? The period that you're in, like barium, is in period 6. So I know it's going to be the noble gas over here, and I'm going to add something that starts with a 6, so 6s something, right? And if you had something in 7, you're going to take the noble gas from period 6, write that, and then 7 something, like 7s, 7p, that stuff. And you guys notice, right? Barium is located over here, right? Barium's located over here, and we ended with an S. So this is called like the S block, which just means like your last electron will be in an S subshell. This is P block, and this is D block. And then there's also these right here, right? The lanthanides and actinides. I don't think we ever touched this, but like this is the F block if you ever had it. So if you had something over here, like it's a good example, like aluminum, right? Then you would have like the noble gas shorthand, and then you would end up with P. So you have like something S something and then something P something, right? So let me check aluminum real quick. Aluminum is in row 3, right? So aluminum would have neon. And then how would I complete this for aluminum? So what's up? Yes, so 3s2, right? 3s2, but aluminum is over here in the P block, so that means we're gonna end with the P. So next in line is 3p. And then the corresponding like row it's in will also tell you like how many electrons are there. So aluminum is right here in the first group. So you know it's gonna be 3p and then 1 because it's in the first group. So that's kind of like what S, P, and D block mean. Let's talk about D block real quick. Like the D block is like your transition metals and stuff like that. And these are like annoying. I'm trying to find one that's not exception. This one has like exceptions and stuff. All right, let's do iron. Can you guys do iron like Fe? Tell me how many or what is the electron configuration of iron? Yeah. So, anyways, this is like general like it's just the usual like you just figure it out however I figured it out, right? But when you deal with stuff, if you look at your periodic table, look at where chromium is. That's the fourth group, right? Fourth column in the transition metals, and the copper column, which is number 9. For chromium, it's gonna look like I don't remember off the top of my head, but it's gonna have like yeah, and there's an argon here. But anyways, you're gonna end with 4s2, 3d4. But what does this look like? This looks like this right here. S, and then you see you have these filled up, and then you have 4 electrons. This is where the exception comes in, where it doesn't like not having one orbital without an electron, right? So what it's gonna do is it's gonna take an electron from the S, right, and just bring it over here. And don't worry about like the spins and all that. It's just like it'll be something. It doesn't matter like if I took from a negative, it would just be it would just match however it's supposed to match. But this means that the proper electron configuration for like chromium is actually going to be 4s1 3d5. And this is not excited ground or anything. I mean, this is the ground state, right? It's not excited or anything like that. This is the normal stable configuration for chromium. And all the stuff in that same group, that same column. Like what else is there? There's like MO, tungsten, that type of stuff. Same thing will apply where they will take from the S orbital and just take it, bring it to the D. So now that's why I mentioned the ninth row or ninth group as well, like copper. Copper is gonna look like different color. All right, copper is gonna be argon, force 2, and then 3D9. Now look at this one. When we draw it out, okay, this one, every single one of these D orbitals has 2 electrons. They're all filled except this last one, right? And it doesn't like that, the fact that there's one, this is one away from being completely full. So same situation is going to apply here where it takes from the S and brings it over. And so that means your most stable configuration for copper is going to be AR 4S1 3D10. Make sure you know this because I've seen it come up a few times. Yeah, really quickly, there's like a term called paramagnetic and diamagnetic. I don't know too much about them, but like basically, if you have something that has all the orbitals filled with electrons, like 2 electrons, it will be diamagnetic, and if it doesn't, it'll be paramagnetic. So let's look at beryllium once again. Beryllium is has 4 electrons, right? So beryllium will look like this, right? It's 1s2, 2s2. So this is your 1s, this is your 2s, and you have your electrons there. Everything is filled up. It's all like even. So this would be something that's diamagnetic. And then if we do lithium, right? Lithium is right before it. Lithium would just be 1s2, 2s1, and that would just look like this right here. This one, it's not all filled up. There's at least one orbital without an electron. So this would be something that's paramagnetic. You can know that something is diamagnetic if it's like at the end of its block, right? Okay, I'm gonna end this here, and then do you guys want to continue? Like, yeah, what's up? What's up? Yeah. Yeah, I know what you're saying. I don't think it matters. Like, yeah, the way I mean, yes, there's like a convention, no way to write it, but I just write it like this. It doesn't matter. They're not gonna test you on that stuff. They'll just test you on, do you know how many electrons are in the orbitals? That stuff. Yeah. Or alpha. Yeah, yeah. Okay. I think that's it for this chapter. Yeah. So it's 8:40.